Today we'll be looking at 4 questions on electricity for the Higher Physics paper. Before we get started, it's a good idea to get your calculator and physics equation sheet because it's important to familiarize yourself with both of these before next week's exam. If you would like to try question 1 yourself first, please go ahead and pause now. Right, the question starts off fairly easy, where you've just been asked to say where you would put a switch to turn off both bulbs at the same time. The answer is obviously M, because if you put it on either of these branches, they would only affect each bulb individually. Moving on, you need to draw a circuit symbol for a switch. You could do this either as an open switch, like this, or a closed switch, like this. Either answer there is fine. Next up, we've got a simple question on current flow. Pause the video if you'd like to attempt this yourself. Now, actually substituting the numbers into this equation that has been given to us, we've got a current I being equal to a charge flow Q of 24 coulombs, as stated in the question, divided by a time of 30 seconds. And that's going to give us a final answer for current of 0.8 amps. When in doubt about decimal places or significant figures, just default to SF. Moving on, we've got another question where they've given us an equation. You typically find this in the higher paper towards the beginning of the paper in question 1 or 2. All we need to do is calculate energy transferred. So substituting the values in, we've got energy E being equal to a charge flow Q of 60 coulombs multiplied by a potential difference V of 3.6 volts, as stated in the question, and that's going to give us a final answer of 216 joules. Now, there's actually a follow-up question we can do on this part, where we could try to find the power supplied by the battery. Now, there are several ways we could do this. If we go back to the equation sheet, looking at the first page where most of our electricity equations are, towards the bottom of the first page, you will notice we've got an equation for power here and 2 more over here. Oh, there too. Really, this one and this one are the same. Now, where all those equations, it's important to know which one to choose. So we are going to go ahead and try the 2 most common ones. Power equals energy over time and power equals voltage times current. Going back over here, if I tried using power equals energy over time, well, I've got an energy transfer of 216 joules. We've just calculated that, but we don't actually know how long that took to transfer that 60 coulombs. We knew that 24 coulombs would transfer in 30 seconds, so we could work it out that way, but it's a bit complicated. It's probably easier then, instead of doing power equals energy over time, to use P equals V multiplied by I, where V of course is potential difference and I is current. The question has given us a value for potential difference of 3.6, and on the previous page it has given us a value for current, which we calculated, of 0.8 amps. So putting both of those into this equation, we've got 3.6 multiplied by 0.8 from the previous page, and when you multiply those together, you get 2.88 watts. That hopefully is just a gentle reminder on choosing an appropriate equation based on the quantities that are given to you. When dealing with electricity, you should have your equation sheet next to you, and you should be looking at the bottom of the first page where most of the relevant equations are located. However, don't just jump to the first one that you see, because often there will be a simpler one later on, so it's important to consider the quantities that you have before starting. Let's move on. So here we've got two circuits, X and Y. One's in parallel, one's in series, and question E asks, how would the ammeter in circuit Y compare to the ammeter in circuit X? Pause the video now if you would like to try this yourself. So the trick to this is you need to calculate the total resistance of each circuit. And to do this, you need to remember that since the components used are identical, we can just assign any random value of resistance to these bulbs to come up with an easy set of calculations. So I could say each bulb carries a resistance of 2 ohms. Just to help me out when working out total resistance, I've just chosen a number. You could choose any other number that works for you. Now, we'll start with the series circuit. In series, current only has one direction in which it can go. It can only go along that one path. And that means that since it's flowing through both of these bulbs, their resistances will have to add. So my total resistance, which I'll write here as R total, is going to be 4 ohms. Nothing too difficult there. But now, let's take a look at the parallel circuit. Here, as current travels through, it reaches a junction, and it has to be split between these two paths, the upper path over here and the lower path over here. Having two paths for current to travel along is a bit like splitting traffic between two roads. It doesn't matter that the roads have some resistance on them. Two roads is still going to get the traffic across faster than just one. Opening up another path for current to travel is therefore going to reduce total resistance. That's really important, so I'll say it again. Having another path along which currents can travel is going to reduce total resistance because it gives another route for charge to flow around the circuit. This means that whilst, for instance, if I only had one bulb, removing this bottom branch, if I only had one bulb, my total resistance here would be 2 ohms. Opening up that second branch for current to flow, having two bulbs and two paths, means that overall resistance drops to becoming less than 2. You'll be happy to know that you're not actually expected to calculate a numerical value for total resistance in parallel, but you are expected to know that it is less than 2 ohms in terms of total resistance for this parallel circuit on the left. This is true in general. So for instance, if I were to draw a parallel circuit with a 1 ohm resistor on the upper branch and a 3 ohm resistor on the lower branch, right now it's got a total resistance of 1 ohm, connecting that second branch, and total resistance drops to less than 1 ohm because all of a sudden current doesn't just have one path to go along, it has two. Now, what was the point of all of that? If we look at our total resistance for X and Y, you can clearly see that X has a lower total resistance than Y. With a lower resistance, we are going to get a higher current flowing through the circuit at the point measured by the ammeter, right at the beginning of each of these circuits. So that means that because circuit X has a lower total resistance, it's going to have a higher current, and vice versa. Circuit Y has a higher resistance, so it will have a lower current, because obviously resistance is the opposition to the flow of current. We're going to then mark out our answer. The reading in circuit Y would be lower on the ammeter because current is lower, as we've stated over here. Moving on to the next question, how does the total resistance of circuit Y compare to the resistance of circuit X? The answer here is, of course, simply total resistance of Y is greater. we had to work that out to figure out the current anyway. Let's move on. If you'd like to pause the video to work this out, do it now. Okay, first up, we're just going to write the equation that links current, potential difference, and resistance. You may still get these questions this year, even though you are given an equation sheet, so please make sure you don't get this wrong. You can write it in symbols, as I'm doing now, where the potential difference equals current I multiplied by resistance R. You could also write it in words if you'd rather. Either's fine, as long as you get it right. Moving on, we're going to calculate a resistance of the lamp. So the safest way to do this is really by substituting numbers into the equation, because you often get a mark for substitution and not rearrangement for these lower mark questions. So putting in the numbers that we've been given, a potential difference of 3.6, we've got a current of 0.8 amps, a resistance R that's unknown, and this can then be rearranged to give us R equals 3.6 divided by 0.8 to give us a final answer of 4.5 ohms. Let's move on. Looking at question 2, if you would like to attempt this yourself, pause the video now. So, in this question, we've got a variable resistor attached to an ammeter and a battery, and the question's telling us that a student investigated how resistance being varied affects the current flowing through a circuit. Predictably, as shown in figure 2 over here, increasing resistance causes current to decrease, and the first question asks us to find the potential difference across the battery. They've given us a value for power and a value for resistance, and when dealing with slightly more complicated calculation questions like this, it's a good idea to label the quantities that you have. So I'm going to go ahead and do that. We've got a potential difference V, a resistance R, a power of 230 milliwatts, that's P. I know that I'm trying to find potential difference, so the first thing I'm going to do is go to my equation sheet and try and find an equation that links potential difference, resistance, and power. So going back to the first page for our equation sheet, looking towards the bottom, I can see I've got voltage equals current times resistance, but that doesn't have power. And I've also got these two equations over here that link power to potential difference, current, and resistance, but there isn't really an equation that links all three. The trick here is to then combine two of these equations. And to know which ones to combine and how to combine them, we're just going to have to start by choosing an equation that gives us the quantity that we're looking for. So in this case, the quantity we're looking for is potential difference, and I know I have resistance, so I'm going to go ahead and use this equation first. Now, going back to our working, I'll write a potential difference V equals I current multiplied by resistance R. I'm going to then put in the values that I have. So I don't have a value for current, but I do have a value for resistance of 36 ohms. It then stands to reason that since I want potential difference, I need to look for a way to find I. And the way to do that is to use another of those equations from the equation sheet, and that's going to be power, P, is equal to I squared R. The reason this equation is useful is it links the quantity that I'm looking for, I squared, to two numbers that I already have, power and resistance. So this is how you should go about this kind of problem. Write an equation that gives you the value that you're looking for, figure out what else you need to find to make it work, and see if there's a second equation that links that quantity to two numbers or more that you already have. Let's finish off the working now. I'm going to substitute a value for power. That's 0.23 watts, just changing milliwatts to watts there. I've got I squared, and I've got a resistance R of 36. Rearranging this equation, I've got I is equal to the square root of 0.23 divided by 36, and that is going to give me an answer of, well, a long decimal, but rounded off, you should get 0.08 amps. Now, I can take this value of current that I've just calculated and substitute it into my original equation over here. So let's do that. I've got 0.08 multiplied by 36 ohms, and that's going to give me a final value for potential difference of 2.88 volts. And that is one way of doing this problem mathematically, combining two equations. Now, there is another method that you might prefer. So the other way you could do this is, of course, by using the graph over here. Typically, when you do need to use a graph to solve a problem, the question will remind you, here they haven't done that, but you can use the graph anyway, no one's going to stop you. And this graph is useful because we know we are looking for potential difference, and we know that equals current multiplied by resistance. This graph gives you a whole range of values that link resistance to current. So a very easy way of solving this would be to pick a well-defined point along this graph. Don't go for a point that you know might be lying off a grid line. Choose something a bit more logical. For instance, this one over here looks good. We can use this point to read off a value for resistance. So let's do that. That has a value of 24 ohms. And we can also use it to read a value of current at that resistance, and that is 0.12 amps. Okay, so now that I've got those two coordinates there, I can just substitute them into the equation V equals IR. Let's go ahead and do that. V equals I, current of 0.12, multiplied by a value of R of 24 ohms. And that's going to give us a final answer of 2.88 volts. And that is a much simpler way to get those 4 marks compared to doing it mathematically. The reason I started with a mathematical method first is often they will ask you this and not give you a graph. So it's really good to know both ways. But when there is a graph, see if you can use it and get some useful information. Let's move on. You can pause the video here if you would like to attempt this yourself. Okay, the question's asking us to prove that current is inversely proportional to resistance. We're trying to show that the student is correct using figure 2. So here we've been explicitly asked to use the graph. It does link to the idea of inverse proportionality in maths, where you should hopefully know that when we say two quantities are proportional, in this case, current and resistance, we can write those quantities like this. Current is inversely proportional to resistance, so that is 1 over R to show inverse proportionality. And that can be rewritten in this way. Current multiplied by resistance is equal to a constant value, and in math you typically write that constant as a K, but here I'm just going to put it in words and write it very clearly to show the examiner that I know that current multiplied by resistance is going to give me a constant value because those quantities are inversely proportional to each other. So, how do I actually prove this using the graph? To read off a line from the mark scheme, you are expected to show that 3 pairs of values give you a constant number. This is just something you have to do. The mark scheme always asks you to pick 3 points, prove it that way. I like to do 4 just in case I misread one of the points. Let's go ahead and do this. So, I'll start with this point over here. It's got a current of 0.24 and a resistance on the x-axis of 12. Picking another point along the line, let's go for this one here. That has a current of 0.08 and a resistance of 36. And one more, just for good measure, like I said, let's pick this one over here. That has a current of 0.06 and a resistance of 48. Now, I'm just going to keep working on this page so it's a bit easier to refer to the points. Starting with the first point up here, let's go ahead and multiply those values of current and resistance. So current 0.24 multiplied by a resistance of 12, and that should give us 2.88. There we go. After all, I times R does equal V, but rarely here we're just trying to show that it equals a constant value. The actual physical quantity isn't important. Anyway, carrying on, we already proved that for this point over here, we get 2.88, so let's just write that down. 0.12 multiplied by 24, giving you a value of 2.88. Doing that again, and this does get tedious after a while, so let's just try and rush through the remainder. 0.08, 0.06, multiplied respectively by 36 and 48. And let's just check those individually. The reason I am checking it individually is if I have misread a number off the graph, I will not get the marks. So I want to make sure that all of these pairs are giving me the same constant value. In the exam, what you'd be expected to do is have essentially this copied over. Now, that would be more than enough for the 2 marks because you have very handily shown that all of these pairs of values give you a constant number as expected according to that relationship of inverse proportionality. But if you do want to write out an explanation, I'll add that in on the side. Again, copying this out from the mark scheme, the product of current and resistance is constant. And I'll just add this on. That indicates inverse proportionality. Okay, let's move on to a somewhat more difficult question now. A switch has been connected incorrectly. Big hint with the word incorrect there. You've been asked to explain how closing the switch would affect the current going through the variable resistor. So right now the switch is open. How would closing that switch affect current flowing through this upper branch? I'll give you a second to pause the video before we go through the answer. Okay, this goes back to what we were talking about earlier, thinking about current flowing from a battery and splitting up at the junction of parallel circuits based on the individual resistances in each branch of the parallel circuit. Right now, with the way the circuit's set up, with the switch being open, no current can actually flow along this bottom branch. Effectively, its resistance is infinite because no current can go along at all. It can't cross the open switch over here. However, when we close the switch, and I'm going to try and draw that on, so let me scribble over the open switch. Okay, Now that switch is closed, current can flow along this path, and all of a sudden, there is a very easy way to get around the circuit. Because going along this bottom path here, there are no components, and effectively, its resistance has gone from being infinite when the switch was open to being 0, because there are no components, so there's basically 0 resistance. The switch itself has a very, very low resistance that can be ignored. Now, what that means is, if you have charge flowing along, it's going to want to travel along the path of least resistance. It's not going to travel along this upper branch anymore. If I actually were to write this out, I've now got a very low resistance, effectively 0 ohms on this bottom branch, and a relatively very high resistance on this top branch over here. The fact that this top branch with the variable resistor has a really high resistance means that current isn't going to want to flow along this upper branch. This effectively acts like a wall in comparison to this shortcut around the circuit. Notice how I said shortcut. When current can take a shortcut around a circuit, we call that a short circuit. Short circuits aren't good. They can be quite dangerous because they lead to overheating. However, that's not what the question's asking us about. It's not asking us about danger. It's just asking us about current flowing through the variable resistor. So let's go ahead and answer it now. First off, just saying that in the first place, current through the variable resistor is, or would be, I guess, almost 0. Because, remember, it's an explain question, so we always need to say why or say because, give a reason when it's an explain question. And the reason here is because, by comparison, it has a much higher resistance than the closed switch. We'll be specific, we'll say it's a closed switch. Which has a resistance of effectively 0. Now, when I answered this question, this is where I stopped, but admittedly, there is a point that I missed in the mark scheme, and that is just to mention that short circuit, about how current can now travel freely along. Let's add that on as our next line. I'll write that in a different color. Current flows through the lower path because the switch creates a short circuit. Now, that's quite a verbose answer because I'm trying to explain exactly how it works. But if you are marking your own work, these are the key points you had to include. You had to say that current becomes almost 0 going through the variable resistor. After all, that's what the question's asking. And you had to mention something along the lines of the switch creating a short circuit. So one mark over there and another mark over there. For that second mark, you could also say the potential difference across the variable resistor is 0, according to the mark scheme, but I'm not sure how you'd figure that out based on the question, to be honest. Let's move on. Looking at question 3. If you'd like to attempt this yourself, as usual, pause the video now. Okay, so this is a question about ohmic conductors, and they've helpfully given us words to choose from. But when this question was asked, Most students actually did quite badly. The correct answers were current through an ohmic conductor is directly proportional to the potential difference across the component, provided that the temperature remains the same. So, ohmic conductors are something that you should hopefully remember from IV graphs, that is current voltage graphs. I'll draw you an example right now. When we talk about fixed resistors and we draw their current potential difference or IV graph, because it's an ohmic conductor where current is directly proportional to potential difference, we would expect a straight line going through this graph, indicating direct proportionality. This is only true if temperature is constant, because typically increasing temperature increases resistance. And a straight line over here indicates that resistance is staying constant. Here, moving on to part B, we've got another IV graph. Remember, your current is I and your potential difference is V. So color coding that on my initial graph, really. That's I in blue. Okay. You've been asked to explain how the resistance of the filament lamp changes as the potential difference across it increases. So what happens to resistance as potential difference goes up? Once again, pause the video if you'd like to try this yourself. There is a very set answer you can give here because it's a common question, so this is really something that's worth remembering. When you have potential difference increasing, that causes currents to increase. We can see that on the graph over here. Potential difference goes up, current goes up. Writing down that first line, as potential difference increases, and I'll color code current. Current increases. Okay, so we know that much. But what happens when current increases? If you think about a conductor with all of its ions located along the metal, when you say that current's increasing, what you're saying is that you've got more charge flowing along or drifting along your conductor in a given amount of time. After all, current is just charge divided by time. If you have more charge flowing along, it's going to be bumping into the ions more, and that's going to actually cause temperature to go up because energy will be transferred from the charge that's drifting through your circuit to the ions of the metal. It's going to cause temperature to increase. So that's going to be our next line. This causes temperature to increase. Notice how I haven't actually given an explanation of how that works. That's not necessary according to the mark scheme. You just need to know that because current increases, temperature goes up as well. What happens when temperature goes up? For the vast majority of resistors that you meet, when temperature goes up, resistance goes up. Think about it this way. If temperature goes up, the ions in your metal are going to be vibrating a lot more, and that's going to make it harder for current to flow through because it's going to be bumping along these ions that are moving back and forth and vibrating about their positions. So temperature increasing makes it harder for charge to flow because the ions are vibrating about. All you need to write in your answer here, though, is you just need to say that resistance increases as temperature rises. Now, this is all that's in the mark scheme, But if you would like to include a line about the ions that are vibrating more as temperature goes up, you can write something along these lines. I'm just going to put this in pink, just in case it's useful for a future question. This is because the ions in the metal vibrate more, making it harder for charge-carrying electrons to drift past. Once again, this bottom line over here is not in the mark scheme, but I thought it'd be useful in case it comes up in a future question. Right, let's move on. Most householders are replacing their filament lamps with LED lamps that are more energy efficient. What does energy efficient mean? Please memorize the answer to this question. It comes up nearly every year in one way or another. Pause the video now if you'd like to try this yourself. The answer that I was expecting was something along these lines. More energy efficient means that a higher proportion of total input power is usefully transferred to output power. And let's break down this answer. Very important word that I've used is a higher proportion. Rarely efficiency is just talking about the fraction of energy that is usefully transferred. And that's the second important word, transferred over here. You're transferring energy from an input to an output. Those are kind of the two key points, and rarely they link back to the equation that is given to you in your equation sheet. Let's take a look at it now. So on the first page over here, without any symbolic equations, so it should be easy to find, you can see that efficiency is useful energy output over total energy input. Rarely these two equations are exactly the same. You're basically just saying you've got useful output over total input. You're just looking at how much energy is usefully transferred from an input or total input into an output. Remember that efficiency has a maximum value of 100%, or if you're working it out, you should get a decimal that is less than 1. Right, going back to that question, just because it's so important, you really should memorize this before your exam. Let's just read it again. A higher proportion of total input power is usefully transferred, special emphasis on useful as well, into output power. Okay, so it's input being usefully transferred to output. Please remember that. Let's move on. Here, we've got a really tricky question. So I will zoom in on this first bit and pause the video now if you'd like to attempt this yourself. Before we start answering this question, it's worth reminding ourselves about what the circuit actually is and how it works. This is called a potential divider, where we've got two resistors effectively splitting up a potential difference between them. That sounds really complicated, but it's not that bad. Think about this circuit where I've got one resistor over here and another resistor over here. So these are basically the same circuit, I've got two resistors here, and I've got two resistors here. I've got a power supply here and a power supply here. Now, let's imagine that cell that I've just drawn has a potential difference of 8 volts. That 8 volts needs to be shared between the two resistors. Its potential difference is going to be divided between them, which gives us the name potential divider for this circuit here. The way in which it's divided depends on the resistances of each individual resistor. It's their ratio. So for instance, let's say one resistor had a value of 1 ohm and the other had a value of 1 ohm as well. We'll start simple. The potential difference then splits evenly between them. So there'd be 4 volts across the first resistor and 4 volts across the second. Nice and easy. But what happens if that ratio changes? So for instance, what happens if instead of a simple 1-to-1 ratio, I've got, for example, 3 ohms over here and 1 ohm over there. This potential difference is going to be divided in a 1-to-3 ratio based on the individual resistance of each resistor. Splitting 8 into a 1-to-3 ratio, that's more of a maths problem. You should be able to work that out. 1 over 4, because 3 plus 1, multiplied by 8, that gives you 2. So we've got 2 volts across the first resistor, and similarly 3 divided by 4 multiplied by 8, that's going to give us 6. So I've got 6 volts across the second resistor. Just to explain what I was doing again, I got 8 because that is the potential difference of the power supply over here. That's what's being divided. I got the 4 in the denominator because I was just adding their resistances, 1 and 3. And I got 1 and 3 for, each individual resistor. Rarely it's a ratio problem. And to check that you've done it right, just like ratios in maths, you can add these values together, 2 and 6, and you should see that you get 8. So what that means is, going to this problem over here, is that 12 volts is going to be split between this fixed resistor here and this light-dependent resistor. But when you add the potential difference across each one, you should get 12. The other thing you need to remember to solve this admittedly very difficult problem is how a light-dependent resistor works. So a light-dependent resistor, I draw a graph over here where the x-axis is brightness, the y-axis is resistance. I'm expecting a graph that looks like this. Lots of resistance in dark, very little resistance when it's very bright. Remember this by thinking about there being lots of resistance in the darkness. So there is resistance when it is really dark, and very little resistance when it's bright. This is kind of similar to how a thermistor works. So the graph that I just drew was that for an LDR. Graph with a similar shape. If I have temperature and resistance over here, a thermistor has that same shape where as temperature goes up, its resistance goes down. Note that that is the opposite to normal resistors, where for normal resistor, its resistance goes up with temperature. That's what we were discussing earlier. Anyway, back to the question. We've got a light-dependent resistor here, and the question says that light intensity decreases. So effectively, we are getting darker. Now, I find this, really confusing to hold in my head. So if I were you, I would literally write it down. Light intensity decreases, so resistance increases. As it gets darker, resistance goes up. There's resistance in darkness. Now, what happens to potential difference? Well, The easiest way to do this is to just assign a random number to start off with. So let's say 2000 ohms to start for the LDR. That would split voltage in a 6-6 split, because right now they've got equal resistance. Light intensity decreases, so resistance is going to go up. This 2000 might now change, let's just guess and say it changes to 6000, 4000, a bigger number. Doesn't really matter. Now, my potential difference needs to split in a different ratio. So, instead of splitting evenly, the potential difference across this resistor is now half that of this resistor over here. So potential difference has to go up because this has a bigger resistance, so it gets a bigger share of the potential difference. Actually splitting it, we might as well do it, why not? It would be 4000 over 6000 for total resistance, multiplied by 12, and that gives us 8 volts. So I'll write that over here. That's 8 volts across the LDR, and 2000 over 6000 gives us 4 volts across the fixed resistor over here. Notice how when I add those together, I get 12 volts, which is the original potential difference at the power supply. Writing this down, as resistance increases, potential difference is going to go up as well. So let's write that. Potential difference increases. Okay. Meanwhile, when we think about current, looking at total resistance, we know that resistance has gone up over here. So total resistance must have increased. And if resistance goes up, then current flowing through the circuit has to go down, because a higher resistance makes it harder for current to flow. So, describing what happens to current decreases. Because, and I'll just write an explanation here, not necessary of course, but I write it down, because total resistance increased. Has the LDR got more resistance, total resistance across the whole circuit increased, making it harder for current to flow. Okay, before I move on to the next question, you might be wondering, where did I get the numbers 4000 from? Doesn't really matter. All I did was I chose a starting value of 2000. That could have been anything. I could have chosen to start with 1000. I just chose 2000. And I did that to give me an easy visualization to think about what happens when resistance goes up, when it gets darker. Really, you don't need to do any of that. You could just say, oh, resistance has gone up. It must be getting a bigger share of the potential difference that's being split between these two resistors. That argument works as well. Right, next question, much easier. What is the resistance of the LDR when the potential difference across it is 4 volts? So let me erase my initial numbers because that might be a bit confusing. We've been told potential difference across the LDR is 4 volts. You need to give the value of resistance and give a reason. I'll give you a second to work that out, so pause the video if you'd like to try it. Okay, so the trick here is to remember that this is a potential divider, and since I had 12 volts to start, that 12 is going to be split between these two resistors. If 4 volts goes there, then I'm going to have 8 volts over here. They add up to give 12. Since 8 is double 4, and this resistor has a value of 2000 ohms, the LDR compared to the fixed resistor must have a resistance that is half of 2000, which is 1000 ohms. So look at how those ratios are the same. 1000 is half of 2000 ohms. 4 volts is half of 8 volts. Adding 8 and 4 together, I get 12. And that's really how I worked out the resistance in the first place. So let's write our answer down. We've got a resistance of 1000 ohms across the LDR. And the reason for that, copying this out from the mark scheme, potential difference is shared in proportion to the resistance in a 2-to-1 ratio. Note that that last bit is not in the mark scheme. I'm just putting it in to remind you about the ratio between both potential difference and resistance over here. Okay, let's move on. Calculate the current through the LDR when the resistance of the LDR is 5000 ohms. So I'll zoom out. Let me erase the previous numbers we were dealing with because they will have changed. Pause the video now if you'd like to work this out. Okay, let's imagine you've seen this and you're completely stuck. What you should start doing is look at what the question's asking you to find. It's asking you to find current. We'll label that. Current is I. You've been given a value for resistance, R. And an easy equation that should come to mind that links these two quantities is V equals I R. But how do you do this when you don't actually have a value for voltage across the LDR? The trick is that the current going through the LDR is the same as the current going all the way along the circuit, because this is effectively a series circuit. What we're going to do, knowing that resistance is 5000 ohms over here, we are going to find total resistance in the circuit, and total resistance, let's write that down. I'll zoom in again. Our total equals 5000 plus 2000, giving me 7000 ohms. So I now have a value for the total resistance in the circuit, and that means I can use the value for the total potential difference over here. That's why I'm doing that, so I can use the 12 volts there. Putting that into the equation, I've got 12 for voltage and a current, I. That's what I'm trying to find. Rearranging this equation, we've got I equals 12 over 7000, giving me a final answer of 1.7 multiplied by 10 to the minus 3 amps. If you ended up writing 0.0017 amps, that's absolutely fine. All it says is give your answer to two significant figures, and both of these answers here are to two significant figures. That was quite a tricky question on potential dividers. Doesn't come up very often, you'll be happy to know, but I do think the general principles are quite useful because it teaches you about how potential difference is shared in between resistors in a series circuit. Just before we move on, I thought I would remind you of the simple fact that in parallel circuits, things are much easier. So if I had a parallel circuit looking like that, doesn't matter what the resistance is on each branch, could be 1, could be 3000 on the bottom branch. Voltage, potential difference, is going to be the same on every branch. So it's 8 volts there, it's 8 volts over there, and 8 volts over there. Potential difference stays the same on every branch of a parallel circuit. So much easier to deal with in terms of potential difference compared to series. Anyway, let's move on. We've got a question on overhead power cables now. It has come up a few times in the last few years, so if you would like to try this yourself, pause the video now. Okay, the questions asked you to explain the advantage of transmitting electricity at a high potential difference. This is sometimes a 1 mark question, and if it was 1 mark, you just say, using a high potential difference means you can transfer energy more efficiently. But you actually need to explain why you're transferring energy more efficiently here. And it links back to this equation in the formula sheet. Power is equal to I squared R. Now, there are many different equations for power, but this is the one that we're using here because it conveniently links power to the resistance of the cables in the national grid to the current flowing through those cables. This power is really the power that you are losing through those cables. So, logically, your cables will have a resistance, not much you can do about that, but logically, you want to lose as little power as possible, so you want a really low current. And that's why we're using a high potential difference. Writing this out as an answer, using a high potential difference leads to very low currents. The key part of this first marking point is mentioning the very low currents because of the high potential difference. You don't actually need the equations to back you up. Just remember this general point. Having very low currents means that we lose very little power, as we've talked about earlier. So, where would you be losing that power? You'd be losing it to your surroundings through thermal energy loss. Let's write both of those points down now. I'll use a different color for this. This increases the efficiency of power transmission because, and I always try and include a because that usually puts me on the right path in an explain question, and it increases the efficiency because less thermal energy is transferred to the surroundings. Now, I've just copied it out from the mark scheme, but really, just to be a bit more accurate, is transferred to the surroundings as heat. Anyway, breaking down the marks here, you would get 1 mark for mentioning the very low currents, 1 mark for saying this increases the efficiency, and another mark for saying that less energy is transferred to the surroundings. So, not too difficult. Let's move on. This question came up last year, so it's well worth attempting. Pause the video now if you'd like to try it. Okay, we're going to start just by explaining how the kite might conduct a charge in the first place, like how the electricity or charge might travel from the power cable over to the kite. Around the power cable, if you imagine the power lines going along between the pylons, there is obviously a very high potential difference, and that very high potential difference leads to a very strong electric field. So around this, there is an electric field that is very, very strong. What can happen because of that strong electric field? The air around the cables can become ionized, and that can lead to the air conducting charge, because when it's ionized, those ions can carry charge. Let's write these points down, talking about the electric field first, and then talking about the ionization of air allowing it to carry charge from one point to another. So, due to the high potential difference, the electric field strength around the cables is very high. So that would get you 1 mark. Moving on to the second marking point, talking about what happens to the air. This causes the air to ionize. Now, if you've been doing past papers, you may have seen this being referred to as the air breaking down or the air becoming a conductor. We can add to our answer here, just to elaborate that. This causes the air to ionize, allowing it to conduct charge to the kite. Now, in last year's question, this would have been enough, but here there is a final mark that many people miss. The question says the person holding the kite could receive a shock if the kite was close to the power cable. So you now need to explain how electricity or electric charge gets from the kite over to the person. Going back to the picture, imagine a kite flying along. What links it to a person on the ground will be the string. Not really sure why that person's holding it with their mouth in the diagram, but we'll ignore that. Anyway, talking about charge traveling along the kite string to the person is what gets us the final mark. So, writing this down, I'll use a different color. And the mark scheme does say, you could say the kite or you could say the string specifically. Conducts the charge to the person and the earth. And if you want to repeat the information in the question, you could say leading to an electric shock, but really, since it's in the question, it's not necessary repetition. All right, that's that question done. Let's move on. Here, we've got a scientist investigating how the potential difference needed for the air to conduct charge varies based on distance between the cable and the earth. There's so much comprehension in that question, there's a lot going on. You've got a distance of, let's say, 0.20 meters. What the scientist is trying to find out is how much potential difference you need in order for the air to conduct charge at that distance. And in this case, that would be 600,000 volts. The first question, C, asks you to draw a line on the figure to show how the potential difference changes as humidity increases. I'll give you a second to attempt this on your own, so you can pause the video now. Okay, it's potential difference needed for the air to carry electricity. So let's actually write that down on the y-axis. Potential difference in volts for air to conduct charge. The question tells us, when humidity increases, the air becomes a better conductor. If something's a better conductor, you need less potential difference to ionize the air in order for it to conduct charge. So you need a lower potential difference at a given distance in order to carry electricity. So on the graph, let's mark out a lower voltage. Doesn't really matter what we choose, as long as it's lower. You should hopefully see that that trend will stay true at any distance, which means my final answer, drawing a line on the graph as the question's requested, should look like this. It's 2 marks, one for drawing a straight line and another for that line being below the existing line. Final question that we're doing, I believe. We've got a cross-section through a power cable, and you need to explain why the current in the steel wire is different to that in the aluminium wire. So take a second if you want to pause the video and attempt that on your own. Okay. Individual wires will behave as if they are connected in parallel. So think about all of these as being parallel resistors. The other important bit of information is they've told us aluminium is a better conductor than steel. So basically it has a lower resistance. It's helpful just to rewrite that information. Aluminium is a better conductor, so it has a lower resistance. Steel has a higher resistance. Explain why the current is different to that in a single aluminium wire. First off, we know they're in parallel, so the potential difference across all of them is the same. Remember what I said about resistors in parallel? Doesn't matter what their individual resistance is, the voltage or potential difference across each one, if it's 8 volts at the source, it's going to be 8 volts across every single one. Let's actually write that down. Even though potential difference is the same across each wire in parallel. So how do we take that and actually answer the question, explaining why current is different in the steel compared to the aluminium? We refer to the resistance, like we talked about earlier. Aluminium has a lower resistance, steel has a higher resistance. So even though the potential difference is the same all the way across, the current is going to be higher along the path of least resistance. Let's write that down. I'll do this in a different color. The resistance of the steel wire is greater, so less current flows through. If you would like to see this as a circuit diagram, let's try and stay color-coded this time. So I'll imagine 3 resistors. We'll give each one a different resistance. So you've got the low resistance ones on the outside, just like the aluminium. And on the inside, we'll have the high resistance 4 ohm one. Now, if I had a potential difference of 6 volts at the beginning, it would be 6 volts along every single branch. But current is what splits at each junction. And that's basically what's happening here. Current has split at the junction when electricity split going into all of these different wires. Let's say I started with 9 amps. And when that splits at the branches, you wouldn't be expected to calculate this, but we'd get 1 amp going through the middle, 4 amps going through the top and the bottom paths. And notice that 4 plus 1 plus 4 gives us the original 9 amps that we had at the beginning. It does show you how the resistor with the highest resistance has the least current, even though potential difference across each branch is going to be exactly the same. We can calculate what that potential difference would be based on the exact numbers that we've used. V equals IR, 1 times 4 gives us 4 volts. 4 times 1 gives us 4 volts again. And 4 times 1 gives us 4 volts once again. And it's a 4-volt battery. So you can see how everything does stay consistent. Potential difference is the same along every single branch. Current splits up at the junctions according to the resistance, where the least current will go along the branch with the most resistance, and the most current will go along the path of least resistance, which is really what this question is trying to tell you. Okay, that is all 4 questions done. I hope you found that useful. These were fairly tricky questions, but don't panic if you weren't able to do some of them. The exam has lots of different problems, and you have been working hard all year. Best of luck for your exams next week, and I'll see you in a few weeks' time. Bye, everyone.